Hello, you are welcome to Basic Mechanics. Our topic for today is equilibrium. My name is Brian Frimpong and I'm your host.
Lesson outline. At the end of the lesson, you should be able to understand equilibrium in terms of all the equilibrium conditions. You should be able to draw free body diagrams in 2 dimensions and in 3 dimensions. And finally, you should be able to calculate for the unknown forces.
According to Newton's first law of motion, if the system of forces acting on a body has zero resultant, the body will remain at rest or move in a straight line with constant velocity. This explains that a body is said to be in equilibrium if it remains at rest, if originally at rest, or has a constant velocity if originally in motion. So the body is originally at rest and it remains at rest, or it is in motion and it maintains a constant velocity. In other words, we can say in equilibrium, the resultant force and the resultant moment acting on the body are zero. So the body will show no tendency to rotate and it will remain at rest, that is static equilibrium, or move in a straight line with constant velocity. All this satisfies Newton's first law, which requires the resultant force acting on a particle to be equal to zero. We can represent this condition mathematically as total forces on the x-axis are zero, total forces on the y-axis are zero, and total moment is equal to zero. These requirements are both necessary and sufficient conditions for equilibrium. You have to take note of that. All physical bodies are 3 dimensions. All bodies in this are 3 dimensions, but we can treat many of them as 2 dimensions when the forces to which they are subjected act in a single plane or can be projected onto a single plane. In situations where this is not possible to project onto a single plane or it acts on a single plane, then you have to treat this as 3-dimensional. When solving equilibrium problems, these are the 3 main steps you have to follow. First, you draw a free body diagram for the problem. Then, you obtain equations of equilibrium for the problem. And finally, you solve the equations and interpret your results. There's this normal student saying that understanding of the question is part of the answer. So first of all, you make sure you read the question at least twice for you to understand the question well. You draw your free body diagram, you obtain your equations, and finally you solve the equations. Now let's take the 3 main steps one after the other. So first of all, let's look at the free body diagram. A free body diagram in physics and engineering can also be called force diagram. It can be represented with the initials FBD, which simply means free body diagram. It is a graphical illustration used to visualize the applied forces, moments, and resulting reactions on a body in a given condition. So the underlying word here is a given condition. So your free body diagram should correspond with the given conditions in the question. The body in question may consist of multiple internal members. So the free body diagram should depict a body or connected bodies with the applied forces and moments and reactions which act on the body. Please note that in some complex problems, you need several or series of free bodies and other diagrams to be able to solve such problems. To construct a free body diagram which will correspond with the conditions on the body, first of all, you sketch the outline shape of the body. That is, decide which body is under consideration and imagine it to be isolated from all other bodies. Step 2. You show all the forces acting on the body. Indicate by means of arrow all the external forces and couples that act on the body. These should include: number 1, the weight of the body. Number 2, all external applied loads. Number 3, reaction at supports from which the body was detached. And finally, forces due to contact with other bodies from which the body was isolated. Step 3. Identify each force.
The forces that are known should be labeled with proper magnitudes and directions.
Letters are used to represent the magnitudes and directions of forces that are unknown. That is how to construct a free body diagram. Let's move on to look at some examples of free body diagrams.
With this diagram, a block of a known mass is resting on the inclined plane.
The mass of the block is m, and the block is exerting a weight. So weight is equal to mass times gravity. That is what we have over there. The inclined plane is also responding to the weight which is being exerted by the block. So the reaction is the normal reaction we have N over there, and the inclined plane there's a force, frictional force, opposing the motion of the block on the inclined plane. That is F. Let's look at the next example of a free body diagram. Over here, a body of mass 15 kg has a force labeled P acting on it at an angle of 30 degrees. At point B, the body is being represented with a dot, and the body is exerting the weight onto the surface, and the weight is W. So weight is equal to mass times gravity. Mass is known and gravity is also known. Therefore, you multiply the mass by the gravity to get the weight. The force acting on the body P is being shown there at an angle of 30 degrees. At point C, we resolve the force P to the x-axis and also to the y-axis at an angle of 30 degrees. Draw free body diagram of the foot lever shown below. The operator applies a force of 20 pounds so that the spring is stretched 1.5 meters. So take a look at the diagram and the solution. On your screen is the equilibrium conditions. Resultant force R is equal to the total forces. That is forces on the x-axis, forces on the y-axis, forces on the z-axis if it is in 3D. Total moment is equal to the total moment to the x-axis, moment to the y-axis, moment to the z-axis. It comes in handy if it is in 3D. So in 2D, you use the useful ones. Below are a summary of the necessary steps to follow in solving equilibrium problems. Reaction at support of rigid bodies must not be ignored in equilibrium analysis. A free body diagram is indispensable in solving problems on equilibrium of rigid bodies. All support reactions must be accounted on the free body diagram in order for the problem to be solved correctly. So this is just like you go about the free body diagram, you get all the necessary, you derive all necessary equations, and finally you solve the problem correctly. Modeling the action of forces in two-dimensional analysis. These are part of the equilibrium conditions. On the left, type of contact and force origin. Action on body to be isolated. The left side is mostly what will be given in the question. Based on that understanding, you derive the one on the right. 1. Flexible cable, belt, chain or rope. On your right, that is action on body to be isolated. The unknown introduced here is labeled T, which replaces the cable. So forces exerted by flexible cables is always a tension, means it's a pull away from the body in the direction of the cable. When a body is in contact with a smooth surface, the reaction, the unknown we introduce here, is perpendicular to the surface and it should act at the point of contact. The unknown introduced, when a body comes in contact with a smooth surface, is simply called normal force. Rough surfaces are capable of supporting frictional force, that is tangential component, and it also supports normal components of the resultant contact R. So your resultant here is R, your tangential component is F, and your normal component is N. There are two forces over there. You introduce two forces. One is the tangential one and one is the normal component. It's just like resolving the resultant force R over there to the x-axis and also to the y-axis. With respect to rough surfaces, we resolve the force, either known or unknown, introduced by the rough surface to the x-axis and also to the y-axis with respect to that angle. So resolving on the y-axis, we get the normal reaction or the normal component, and resolving on the x-axis, we get the tangential component, which is the frictional component. A roller support is equivalent to smooth surfaces, that is frictionless surfaces. It can only exert a force, one force, that is perpendicular to the supporting surface, the point of contact. The magnitude of the force is the only unknown introduced in your free body diagram when the support is being removed. A freely sliding guide is also equivalent to a smooth surface. It can support force normal to the guide, one force. A pin support introduces two unknowns, the magnitude and the angle that specify the direction of the magnitude. But more commonly, the two unknowns are chosen to be perpendicular components of the magnitude, that is Rx and Ry. A pin connection goes for free to 10 pin and pin not free to 10. For a free to 10 pin, the connection is capable of supporting the force in any direction in the plane normal to the pin axis. Therefore, we may either show two components, Rx and Ry. Rx is the resultant force being resolved at the x-axis. Ry is the resultant force being resolved at the y-axis. P not free to 10 supports the Rx and the Ry and also supports a couple. A building support or fixed support prevents all motion of the body at the support. Horizontal motion, vertical motion, and rotational movement of the body. A force prevents the horizontal and vertical motion of the body, and a couple prevents the rotational movement of the body. Therefore, for a building support, there are three unknowns which should be introduced in your free body diagram. That is the magnitude of the force and direction of the force, which more commonly we use two components to represent them, the Rx and the Ry. And the third unknown is the magnitude of the couple. Gravitational attraction. Weight is equal to mass times gravity, and this acts towards the center of the earth through the center of the mass G. This always acts downwards. Spring force is tensile if spring is stretched, and compressive if compressed. For a linearly elastic spring, it is being replaced with an unknown perpendicular to the body at the point of contact of the spring. That is the end of section 1 of equilibrium. Thank you very much. Stay tuned for section 2. Drop all your questions at the comment section. Thank you.